Okay, we're now going to start chapter 4, which is on exponential and logarithmic functions. And so exponentials are a type of expression that we didn't study in pre-algebra, right? So everything we've talked about in like the official algebra course, starting with chapter 1 up to this point, has involved expressions. So expressions aren't equations or inequalities or functions. So it has involved expressions that we worked with in pre-algebra. So powers, x to the first, second, third, x to positive integer powers, x to negative integer powers, x to rational powers. So that includes radicals, dividing polynomials, so rational expressions, right? So all of the equations and inequalities we worked in chapter 1 and all of the functions that we've studied so far have involved terms from those types of expressions. But in chapter 4, we're going to be introduced to a new type of expression, which is the exponential. So like 2 to the x. Not x squared, but 2 to the x. And then we're also going to look at the inverse of exponentials. So that's what logarithms are. And so the inverse meaning, if we had x squared or x cubed, well, then the inverse operation was, like the square root of x squared or the cube root of x cubed. And so what we're going to talk about first before getting into exponentials, we want to look at this idea of an inverse of a function. And that's what we're going to talk about in this opening section of chapter 4. Okay, identify one-to-one functions. Throughout our study of algebra, we have made use of the fact that the operations of addition and subtraction are inverse operations. For example, adding 5 to a number and then subtracting 5 from the result gives us the original number. Likewise, multiplication and division are inverse operations. We now look at the concept of an inverse function. Okay, so if you start with a number a and you add 5 to it, and then you subtract 5, you get the original number back. So addition and subtraction are like inverse operations. Same idea with multiplication and division. If you multiply a number by 5, and then you divide that result by 5, you end up with the original number. Multiplication and division are inverse processes. So now we want to look at the idea of an inverse function. Changing currency is an important consideration when traveling abroad. For example, traveling between the United States and several countries in Europe would involve changing American dollars to euros and then changing back for the return trip. Fortunately, we can use a function to change from one currency to the other and then use the function's inverse to change back again. Suppose that 1 American dollar can be exchanged for 0.8 euro, then f of x is equal to 0.8x gives the number of euros that can be bought from x dollars. G of x is equal to x over 0.8 gives the number of dollars that can be bought from x euros. Tables 4.1 and 4.2 show the values of f of x and g of x for several values of x. Okay, so if 1 American dollar can be exchanged for 0.8 euro, then to see how much euro you have given a certain amount of American dollars, you multiply the amount in American dollars by 0.8. But if you want to go the other way around, if you had a certain number of euros and you want to convert that to American dollars, then you say, so you've got, okay, let's come back. If you have a certain amount of dollars and you want to convert that to euros, you say you've got X dollars times the fact that for every $1, there's 0.8 euro. So this is in dollars. The dollars cancel. You're left with euro. So f of x is equal to 0.8 times x. Now, if you have a certain number of euros and you want to convert that to dollars, you say x times x euros, and we know that there's 0.8 euros. The euros cancel for every $1. So if we multiply this out, it's x over 0.8. Okay, so but you see it's two separate functions of just the same input, right? You have f of x is equal to 0.8x, and then the separate function g of x is equal to x over 0.8. Okay, and so it says in this example, the functions f and g are inverses of each other. And we observe several interesting characteristics about inverse functions, right? So these two functions it's saying are inverses of each other. So what are some characteristics of inverse functions? By listing the ordered pairs that they wrote out in the tables, in the two tables, because this was $100, $150, $200, $250 converted to euros, and then that's the same euros converted to dollars. So if you put those ordered pairs here for f and g, notice that the x and y values are reversed, right? So that these, when you to go from one function to the other, they're just flipping the columns, right? Here it was $100 is 80 euros, but for g, 80 euros is $100. So for a function and its inverse, the values of x and y are interchanged. This tells us that the domain of a function is the same as the range of its inverse and vice versa. That makes sense. From the graphs of f and g, we see that the corresponding points on f and g are symmetric with respect to y is equal to x. So that's interesting. The points are like they're symmetric with respect to the line y is equal to x. They've been flipped about the x-axis. When we compose functions f and g in both directions, the result is the input value x. In a sense, what function f does to x, function g undoes, and vice versa. So it says we're going to compose functions f and g. So the composition of functions, right? Remember f of g of x, right? So if we come here, f of g of x is equal to, that's f of g of x, right? That's, let's see, it's 0.8 times g of x, so the result is x. G of f of x gives you the same result, x. Okay, so to get a sense of this, let's say that f of x is equal to x cubed, and g of x is equal to the cube root of x, right? So if you made a table of x's and f of x's, so 1, 2, 3, let's just do that. So that this is 1, 8, 27. Okay, you could input those f of x's into g of x, and you would get 1, 2, 3. You would undo, you could use g of x to undo what you did with f of x. Right? You see how we flipped these two? But like, yeah, we could have chosen some random inputs for g of x that were just independent from this, and it wouldn't have looked like anything. But the idea is with an inverse, we could take the outputs of one of the functions, input them into the other function, and undo what was done. So like we could do the same thing with, so g of x, we could say, so let's do 1, 8, 27 results in 1, 2, 3. And then we could input that into f of x, 1, 2, 3, and it undoes it. 1, 8, 27. You see? So f of g of x, the cube root of x cubed is x. That's f of g of x, right? And then, or you could say g of f of x is, see, these functions are inverses. Okay. The inverse of any relation is found by interchanging the values of x and y in the relation. However, the inverse of a function may itself not be a function. For example, consider f is equal to the 2 points 1, 3 and 2, 3, shown in blue in figure 4, 2. There's a function, those 2 points. The inverse is the set of ordered pairs 3, 1, 3, 2, shown in red. So, yeah, you still just, you look at the line y is equal to x. This is still just reflected about y is equal to x, you see? But with the inverse here, that's not a function anymore, right? Here it was a function, now it's not, because it doesn't pass the vertical line test. You've got the more than one input for a single, more than one output for a single input. Okay, so the function 1, 3, 2, 3 has 2 points that are aligned horizontally. When the x and y values are reversed to form the inverse, the resulting points will be not aligned horizontally, but aligned vertically, and will fail the vertical line test. Thus, a function will have an inverse function only if no points in the original function are aligned horizontally. So it says it will have an inverse function. This does have an inverse. This is its inverse. But it's not an inverse. But it's saying, what does it have an inverse function or not? This doesn't have an inverse. It has an inverse, but doesn't have an inverse function. And so, okay, the function a function will have a function will have an inverse function only if no points in the original function are aligned horizontally, right? So it's a function. Let's think about what they're saying there. A function, okay, a function. So we're thinking about a function. So if it's a function, it doesn't have any points aligned vertically, right? So a function will have an inverse function. So its inverse will also be a function that its inverse will also be a function. So its inverse will also not have points aligned vertically. Only if no points in the original function are aligned horizontally. This is the original function. It is a function, but since it has points aligned horizontally, that means that if you take its inverse, it's going to have points aligned vertically, which means it's not, the inverse isn't a function. That is, no two distinct points on the function may have the same y value. In such a case, the function is said to be one-to-one. So when we went through the definition of a function, the big idea was that you're allowed to have multiple inputs could map to the same output, which made sense. Like if you think about a robot or something, that's the example that we talked about. Yeah, you could have a robot that there's two different inputs, but it does the same thing. You know, it's like you think about if-then statements, but let's say it's going to make coffee. Well, if you wake up at 7 o'clock, make coffee. If you wake up at 7:15, also make coffee. But if you wake up at another time, I'm just making all this up. But like it makes sense for like an ATM machine or something to have, for different inputs, to have the same output. However, the thought exercise was that, but you couldn't have the same input mapping to multiple outputs, because then it would like break. You know, you can't say, give the person, here's an input, give the person both $20 and $50. Well, it doesn't know what to do, right? But you could have two different outputs two different inputs that both say, give the person $20. Now, however, if the function is going to have an inverse function, then now in that case, you can't have separate inputs mapping to the same output if it's going to have an inverse. And that's the idea, because what happens is if you've got, you know, the input 1 maps to 3, and then the input 5 also maps to 3, that's a function. But if you take the inverse and flip these, you've got 3 to 1, 3 to 5. There you go. It's not a function anymore. Okay, so for a function to have an inverse, the function needs to be what they're calling here one-to-one. A function f is one-to-one, is a one-to-one function if for a and b in the domain of f, if a is not equal to b, then f of a is not equal to f of b. Or equivalently, if f of a is equal to f of b, then a is equal to b. So let's read this slowly here. A function f is a one-to-one function if for a and b, these are two inputs in the domain of f, if a is not equal to b, then f of a is not equal to f of b, or equivalently, if f of a is equal to f of b, then a is equal to b. This is just a fancy, mathematically precise way of saying that for a function to be one-to-one, you can't have separate inputs mapping to the same output. Now you might say, well, wait a minute, but they didn't talk about, what about you can't have the same input mapping to multiple outputs? Well, that's already implied that that's true because they're saying this is a function to begin with. We're saying, well, no, they're saying here, it's we're starting with a function. So if we're starting with a function, that's already the case that the same input doesn't map to, or that a single input doesn't map to multiple outputs. So we're starting with that. And then the rest of this is just a fancy way of saying you can't have separate inputs mapping to the same output for a function to be one-to-one. Okay? And we can see that for a function to have an inverse function, a function can have an inverse, that's not a function, but for a function to have an inverse function, it needs to be one-to-one. Okay, the definition of a one-to-one function tells us that each y value in the range is associated with only one x value in the domain, which for a regular function, that's not a requirement. This implies that the graph of a one-to-one function will have no 2 points aligned horizontally. So we had the vertical line test to decide if a relation was a function. Now we're going to add the horizontal line test to see if that function is one-to-one. So you'd have a relation, and you'd first start by testing to see, is it a function? If it's not a function, then it can't be a one-to-one function, right? We're doing a horizontal line test for a one-to-one function. If it doesn't pass the vertical line test, then it's not a function, so it's definitely not a one-to-one function, right? So it passes the vertical line test, it is a function. Then you use the horizontal line test to see if it's a one-to-one function. A function defined by y is equal to f of x is a one-to-one function if no horizontal line intersects the graph in more than 1 point. Yeah, just like the vertical line test, but it's with a horizontal line. If a horizontal line intersects the graph at any horizontal line, it doesn't matter where it is. If it intersects the graph at more than 1 point, then it fails the horizontal line test. Okay, so they give an example problem on this here, but I think that's pretty simple. But we'll work example problems in the next video. Okay, you can see it fails the horizontal line test, but it passes the vertical line test. These are all functions. Passes the horizontal line test. It passes the horizontal line test, but it's not a function. So this is not how can this be a one-to-one function if it's not even a function to begin with? Now here they do algebraic methods to determine whether a function is one-to-one. They're using that mathy definition of a one-to-one function. I guess we can go through these. So show that this is a one-to-one function, or determine whether it is or not. We must show that if f of a is equal to f of b, then a is equal to b. So I guess we could go. Let's come back. So okay, yeah. Let's think about exactly what this is saying here. So for a and b in the domain of f, and so here when they say a and b, this is like any x values, right? You're going to show this in general. This for any a and for any b, for any x, for any two separate x values in the domain of f. If a is not equal to b, then f of a cannot be equal to f of b, right? Or else you've got two separate inputs mapping to the same output. Or it says equivalently, if f of a is equal to f of b, then a needs to be equal to b, or else, yeah, or you have the same problem. So they're showing in this example, they're showing that algebraically here. Okay, so what they do is they just say that, okay, if f of a, you can use either one of those statements. If f of a is equal to f of b, then a is equal to b, or if f of a is not equal to f of b, then a is not equal to b. They use the second statement. So they take f of a and set it equal to f of b and simplify and get a is equal to b. And this is true for, a and b are any real number. So this is true for all real numbers. So it's 1-to-1. Okay, now here, let's assume that f of a is equal to f of b. So that means we've got a squared plus 1 is equal to b squared plus 1. Subtract 1 from both sides. A squared is equal to b squared. Okay, take the square root of both sides, you get a is equal to plus or minus b. So they're not necessarily, they could be equal, but they might not be. You could plug in a and minus b, and f of a is equal to f of b. So that shows it's not a, it's, you could have the same input, or no, you could have separate inputs mapping to the same output. I could plug in a, positive a, and negative b, and f of a is going to be equal to f of b. So this is not one-to-one. Okay, now let's determine whether two functions are inverses. So yeah, we haven't officially defined what makes a function an inverse function. What's the official definition for an inverse function? Okay, we now have enough background to define an inverse function. Definition of an inverse function: let f be a one-to-one function. Okay, so the function, we have f is one-to-one, then g is the inverse of f if the following conditions are both true. F of g of x is equal to x for all x in the domain of g. G of f of x is equal to x for all x in the domain of f. So, yeah, what they're saying here is if f is one-to-one, that means it's going to have an inverse function, an inverse function. And f can be not one-to-one and have an inverse. It's not a function, but if f is a one-to-one function, then it has an inverse function. And now it's saying here that there's another function g that doesn't have to be the inverse of that one-to-one function, right? You could have g could be any function, but g is the inverse of f based on the following conditions: f of g of x is equal to x, and g of f of x is equal to x for all x in the domain of g, for all x in the domain of f. Okay. So that's it. If you first have a function and you test to see if it's a one-to-one function. If it's a one-to-one function, then it has an inverse function. And that inverse function you can find by if f of g of x is equal to x for all x in the domain of g, as well as g of f of x is equal to x for all x in the domain of f, then g is the inverse function of f. We should also note that if g is the inverse of f, then f is the inverse of g. Right? If g is the inverse of, if you find that f is a one-to-one function and you get its inverse g, then the inverse of g is also f. That must be the case. Furthermore, given a function f, we often denote its inverse as f to the minus 1. So given a function f and its inverse f to the minus 1, the definition implies that, yeah, f of f to the minus 1 of x is equal to x, and f of minus 1 of f of x is equal to x. Okay, so determining whether two functions are inverses. Determine whether the functions are inverses. Okay, so now here they determine whether the functions are inverses. F of x is equal to 100 plus 12x, and g of x is equal to x minus 100 over 12. How do you determine whether the two functions are inverses? Well, we're first going to make sure that these are one-to-one functions. Well, or, you could just start with saying just pick either one of these. Maybe see, is f of x a one-to-one function? But you can tell if g of x is going to be if it is one-to-one, if g of x is going to be its inverse, then it also is going to have to be one-to-one, because then if g of x is the inverse of f of x, that means that f of x is the inverse of g of x, and a function can't have an inverse if it's not one-to-one. So you could check both, but but you wouldn't, if one of these wasn't one-to-one, then neither of these are either of their inverses. So however you want to do it, but I think that what they're going to do is they're going to check to see if this is one-to-one, and then you're just going to plug in, you're going to do f of g of x, and you should get x. Then you're going to do g of f of x, and you should get x. So let's take a look. F of g of x, you get x. G of f of x, you get x. Now, they didn't check to see if the functions were one-to-one. I guess you don't have to. Let's see, the other problem they did, h of k of x, and they got the cube root of x cubed minus 2. So the functions weren't inverses. So, yeah, I'm not sure if it's the case that if you find f of g of x is equal to x and g of f of x is equal to x for all x, then that the only way this could happen is if f and g were both one-to-one functions. Because they didn't test, to me they needed to test first to see if f of x was a one-to-one function, because maybe these criteria are satisfied, but if it's not, if one of the functions is not one-to-one, then there's no inverse. But yeah, they don't mention that here. I guess my guess would be that if you didn't have a one-to-one functions, then this simplification wouldn't work. That's probably what the case is, but I'm not stating that officially. Again, I would guess that if you had if f wasn't a one-to-one function, let's say f wasn't a one-to-one function, then doing f of g of x and getting x and doing g of f of x and getting x wouldn't happen. That couldn't happen. So, but they don't state that officially. Okay, finding the inverse of a function. For a one-to-one function defined by y is equal to f of x, the inverse is a function y is equal to f of minus 1 of x that performs the inverse operations in the reverse order. The function given by f of x is equal to 100 plus 12x. Yeah, so this is, remember, this is like if you had f of x is equal to x cubed and g of x is equal to the cube root of x, then this can take all of the outputs of f of x and turn them back into the inputs. It performs the inverse operations in reverse order. That's kind of a confusing statement. But yeah, the idea is the inverse of f of x is going to could take the outputs of this function, take them in as inputs, and turn them back into the original inputs, right? You have x f of x, and then you've got x g of x. This function can take these outputs as inputs and turn them back into the original inputs, and vice versa. I could flip this. This function could take the g of x outputs as inputs and turn them back into the original inputs. Okay, the function given by, let's see, f of x is equal to 100 plus 12x multiplies x by 12 first, then adds 100 to the result. Therefore, the inverse function is going to subtract 100 from x first and then divide by 12. Yeah, that's interesting. So, performs the inverse operations in reverse order. So this is another way of looking at what an inverse means. So the function given by f of x is equal to 100 plus 12x. What does this do? If we're reading from not left to right, but from right to left, it multiplies. Well, no, we're not reading from. It's not reading from left to right or right to left. The function given by f of x is equal to 100 plus 12x. What does it do? Well, you have an input. Like, we're not reading. It says it multiplies x by 12 first. Why is that? We're not like reading from right to left or anything. You input the x, and so you're following the x, right? The x is here. What happens to the x first? It gets multiplied by 12, and then 100 gets added to that result. So what is the inverse going to do? The inverse is going to go in reverse order. It's going to subtract 100 from x and then divide by 12. Interesting, right? You do the inverse operations in the reverse order. The inverse operations. So subtracting 100 is the inverse from adding 100. Dividing by 12 is the inverse of multiplying by 12. But you do that in the reverse order. Very interesting. To facilitate the process of finding an equation of the inverse of a one-to-one function, we offer the following steps. So yeah, this is the more simple way to get an inverse. You don't have to go through these mental steps of like doing the operations in reverse order, but I think it's really interesting to be able to think about an inverse this way. I think that's very intuitive. So I think we're going to work some example problems doing this, but if you want to do the quicker, simpler method of finding the inverse of a function, what you do is, for a one-to-one function, the function you have needs to be one-to-one. Check if it's one-to-one. If it's not, then there's no inverse. The equation of the inverse can be found as follows. Yeah, replace f of x by y, interchange x and y, solve for y, and then replace y by f of minus 1 of x. This makes sense, right? What you're doing is, if you've got f of x is equal to x cubed, okay? And you want to find its inverse. Well, we check to see if it's one-to-one. This is one-to-one. So they're saying you do this. Say, replace f of x with y, and then flip this. Do change y and x. So kind of like screen this off and do this, right? Switch y and x. Solve for y. So y is equal to the cube root of x. Now just replace y with the inverse symbol. And that's it. You're done. And why does this make sense? Well, because the idea is you're just reversing the function, right? You're going in reverse. You have x going to f of x to start with, but you're thinking about, okay, but what if I wanted to do this input here and get this? Well, this is exactly what you would do. You just flip the symbols and solve for x as a function of y in a sense, but yeah, you're solving for x as a function of y, but then you're just flipping the symbols to where it's still just it's a function of x. That's exactly what you're doing. You're solving for x as a function. You're taking a function, solving for x as a function of y, but then just flipping the symbols back to where you have just like another function of x. Because it's like this. You're not going to be, if you had a parabola, okay, that's a function, right? And you solved for, well, this doesn't pass the horizontal line test, but so it doesn't have an inverse, but you solved for x as a function of y, you'd get this. Okay? But then you could, instead of saying having x as a function of y, you could just make this a function of x again, right? Well, it's not going to be a function. It's going to be, have a plus or minus in it, but that's the idea. Okay? So that's how you do it algebraically, which is the easiest way to do it. But again, I think it's really cool to be able to understand this mental exercise here. So, okay, write an equation for the inverse function of f of x is equal to 3x minus 1. So, yeah, this is just, you say y is equal to 3x minus 1. Replace x and y. I'm going to screen this off. Now, solve for y, x plus 1. Y is equal to x plus 1 over 3. Now just replace y with the inverse symbol. There you go. Okay. The key step in determining the equation of the inverse function is to interchange x and y. By so doing, a point AB on f corresponds to a point BA on f minus 1. This is why the graphs of f and f minus 1 are symmetric with respect to the line y is equal to x. Okay, yeah. The key step let's read this again. The key step in determining the equation of the inverse of a function is to interchange x and y. By doing so, a point AB on f corresponds to a point BA on f minus 1. That's why they're symmetric. So here, this was, let's see, this was the line 3x minus 1. What you're doing, what we did was we took the original x and y, that's here, and we flipped it to this. But we just changed the notation to make this like another function of x, right? We end up switching the symbols back. But so what you're doing is you're just taking that, it's symmetric about y is equal to x because you're just flipping the coordinates, right? That's why all inverses are they're flipped about the x-axis, not the x-axis, about y is equal to x, about y, not the x-axis, y is equal to x. They're flipped about y is equal to x. The line y is equal to x. Okay, right. An equation for the inverse function for the one-to-one function defined. So they do the same process here. And yep, so we'll work a bunch of examples for a function that is not one-to-one. Sometimes we restrict its domain to create a new function that is one-to-one. So yeah, this is done every now and then. One good example is inverse trig functions. So given m of x is equal to x squared plus 4 for x is greater than or equal to 0, write an equation of the inverse. So yeah, this doesn't, m of x is equal to x squared plus 4 doesn't pass the horizontal line test. But if you restrict the domain for x is greater than or equal to 0, it does pass it is a one-to-one function. Okay, so there's x squared plus 4, but it's not one-to-one. But here with that restriction, it is one-to-one. And so what happens, well, if you go through the whole process of flipping, the algebraic process, replacing m of x with y, flipping the variables, etc., normally you would get, like, it would say plus or minus and the something, and that's where the issue comes in, where it's the one-to-one issue. But we don't have to worry about the minus because we have this restriction, right? So when they flipped x and y, it changed from x is greater than or equal to 0 to y is greater than or equal to 0. And then here, this is y is greater than or equal to 0, so you can remove the minus, and then boom, there it is. There's m of minus 1 of x. And then you see there's the original function with the domain restriction, and then there's the inverse with that same domain restriction, x is greater than or equal to 0. So yeah, we do this with inverse trig functions. The trig functions are not one-to-one. So like the sine function is not one-to-one, right? But with the domain restriction, we're able to get inverse trig functions. Okay, let's see. Here's another example. The function f is a one-to-one function, and the graph is the same as the graph of y is equal to square root of x with a shift 1 unit to the right. Okay, yeah, because you can't input a negative value into the radical. When defining the inverse, we will have the conditions that x is greater than or equal to 0 and y is greater than or equal to 1. Okay, because here f of x is equal to square root of x minus 1. The x has to be greater than or equal to 1, and y, the range is going to be y is greater than or equal to 0. That's the range. Then they flip the variables here. So now y is greater than or equal to 1 and x is greater than or equal to 0. Square both sides and solve for y. And let's see, f of minus 1 of x is x squared plus 1, but x is still has to be greater than or equal to 0. We can't remove this restriction here, right? The restriction x is greater than or equal to 0 on f of minus 1 is necessary because f, the original function, has the restriction that y is greater than or equal to 0. Furthermore, y is equal to x squared plus 1 is not a one-to-one function without a restricted domain. Okay, so yeah, you can see there's certain situations where you need to be careful with the domains. So yeah, these last two examples we're going to want to work some example problems in the upcoming videos to go through this clearly. Here, there was a domain restriction. You turned the original function wasn't a one-to-one function, but with a domain restriction, you turned it into a one-to-one function and found its inverse. Here, the original function was one-to-one, but when you got the inverse, that function wasn't one. This was, okay, here the original function wasn't one-to-one, but its domain was all real numbers, x squared plus 4. But you applied a domain restriction to make it one-to-one, and then got the inverse. Here, this function was one-to-one, but it had a domain restriction. And then when you found the inverse, you got some function that wasn't one-to-one, but when you factor in the original domain restriction, it is one-to-one. So you just have to state the domain and range of the original function and the inverse correctly. And so we're going to work example problems to illustrate this.